Hello, everyone. Welcome to another episode of Workshop Wednesdays. I am Chanel, founder and CEO of Mentor Me Collective, and I'm also your host today. So I'm super excited to see you all tuning in. Go ahead and let us know where you are tuning in from. Drop it right in the comment section. And we're excited to obviously highlight you all as well. Today, we have a very special guest with us who is going to be sharing some incredible insights. And of course, as you know, AI has been the talk of the town, the lab, the country, honey, all in the streets. And so we want to make sure that you all have really awesome insight as well to make sure that as you sojourn whichever career you'd like, you obviously can navigate that as well and understand how AI impacts the infrastructure too. So, before we fully go ahead and jump in, for those of you who are new to Mentor Me Collective, we are a community dedicated to empowering first generation individuals with knowledge, confidence, and skills in order to help them to pursue their passions, achieve their dreams, and make a positive impact on society. We focus on mentorship, education, and community. We host these wonderful workshops to provide valuable insights to you all as well. And of course, giving you opportunities to develop practical skills, connecting you with experts like this wonderful host that we have today as well. Tonight, we're diving deep into an amazing topic that is absolutely critical for anyone, again, working with AI, the network's critical role in AI infrastructure. So let's be honest, again, AI is amazing, but without a solid network, it is like a supercharged engine with no fuel. Okay, so tonight we have a fantastic opportunity to lean into a wonderful expert who knows this stuff inside and out. We are going to be joined by an amazing network engineer at Google, specializing in network automation and performance. He's not just talking the talk, he's living it, working on cutting edge network solutions every day. So, without further ado, I definitely want to welcome the most incredible Munachimso. Am I saying that correctly?
Good afternoon. Yes, you're good enough, but it's Munachimso.
Oh, Munachimso.
Yes.
That
But
is
everyone calls me
beautiful.
Muna.
Well, that is beautiful. And I'm so excited to formally meet you on here and also highlight your experience and your story. So tell us a little bit about you, Muna.
Okay. What do you want to know?
I guess,
Any?
yeah, like how did you get started in as a network engineer?
Okay. I think personally, it was from. I think because I'm originally, it might be obvious from my accent, but I'm originally from Nigeria, and
Hey,
so I came to United States to study, and my degree was computer networking and IT. So I always knew I wanted to do something computer, but I wasn't sure what exactly. Is it computer science? Is it computer engineering? Then I came across this program, oh, computer networking and IT. Then just the idea of understanding how the internet and everything connects was just like, oh, this looks interesting. Then I went for it, and it has just been just continuous from there, like going deeper and deeper into the networking field, and just loving it every day. Well, yeah,
I love that.
that's it.
Well, I think that's absolutely incredible. So you can go ahead and share your screen by tapping on the little present icon. And once I see it pop up, I will allow you to take the stage.
I
While
mean,
you take your time. While you do that, I'll just say hello to our audience. Hey, hey, everyone. Welcome for tuning in. Those of you who are tuning in, just go ahead and give us a nice thumbs up button if you're on YouTube. If you're on LinkedIn, go ahead and like as well. Also, LinkedIn folks, go ahead and comment. Let us know that you're tuning in as well. Most of us are joining the party on YouTube, but we are more than happy to have all cousins from all of our cousin social media platforms too. So welcome you all. Awesome.
okay.
All right. Looks amazing. Over to you.
Thank Yeah, thank you. Okay, so hello everyone. So for this workshop, I'll be going through the network critical role in AI infrastructure. Um, okay. So my idea is not just to say, oh, AI networks, so beautiful. And oh, I want to give you a clear understanding of what it is when you say AI infrastructure. Exactly what do you mean? So I'm going to go down from the very basics. Start with okay, what is AI infrastructure? Then I'll give you intro to networks as a whole. Then I'll move into networks within a system because these are the core fundamentals to now understand where we are today, and we go all through until enter the AI network infrastructure. So these are like, so I'll be going through in detail, but I've tried my best to make these slides very easy to understand, and I hope I do a great job. So when you look at AI infrastructure, what do you mean? So basically, AI infrastructure is about providing the necessary resources to make the computers have like intelligent behavior. So we know how like right now everybody uses Gemini, ChatGPT. You put in questions and it's smart. So that is because of a lot of processing power from compute processing to storage to networking. There's a lot of processing, and this large amount of resources enables like complex algorithm, able to go through large data sets, process it, and make and deduce intelligent action from that. And but all that is possible because of the high performance networks that are connecting these resources. Like like Chanel said in the beginning, you can have these huge compute, huge servers, but if they're not connected to anything, they're as good as a box sitting down in the garage. So like I mentioned, so networking is that piece that connects everything together. I see it as the enabler of storage and compute, and it's from before AI. From like when you think of networks, it could be connecting to the internet. Whatever it is, AI is an enabler to compute and storage. It supports massive storage, massive CPUs, that and processing power. So that's I see network as that unsung hero because everybody, especially like in fields today, you see like, oh, software engineer, cloud engineer, a lot of buzz in those fields, but not a lot of buzz in the network engineering space. And I feel that is very unfortunate because without networking, everybody, like, we are as much important, if not more. But yeah, so I see AI networking as the unsung hero. So starting from the bare fundamentals, why do we need networks? Networks are basically networks help for communication between computers. You have your computer in your room, and you want to speak with your friend in a different country. You go online, you send a message. That communication is done through networks. You can even in the same office, you can share resources like printers. You have your local network that can do that, and you even have, and it's good to point out that this kind of networks, like when you think of a network, you see an individual computer that is on its own. It can perform its functions like your laptop. It's on its own, can perform its functions, and you want to communicate with another separate computer which does its own functions. So that is how most of us see networks, and I'm going to broaden our minds away from that a bit and see networks much more. So now when you look at a computer on its own, not connected to a network, or not connected to like the internet, you might not necessarily think, oh, net there's anything that has to do with networking there. But I'm going to draw a good analogy from this to lay my points as we move on. So when you have your computer, like a major computer has three major components: your process, your computer, like CPU or GPUs. Then you have the memory, and you have the storage. And these, like in a regular computer, your system unit, your laptop, your phones, all these three components exist, and they are connected through the motherboard. So you have all of them connected through the motherboard, different through like PCIe ports for your memory. You have SATA ports or SCSI ports for your hard disk. So all these things are connected. But in the motherboard, the system that makes these components communicate together is called the bus system, which I want to I want to say it as a mini network, or like a it can be, it's you can have it. It does the work of a network by attaching resources together. So through the bus system, like if you see this picture I put, the motherboard has these lines. If you zoom into a motherboard, you see all these lines, and lines connected through all the different components. So that is the bus system, and I like to see that as a network, because that is does the job of a network, which is um sorry, which is allowing different to communicate. Now let's now look away from our regular computers, because I want to give that example so you to just see that idea of a network. That a network is not just connecting multiple different computers, but within a computer system, a network lives inside there. So now, when you now, as time went, not instead of just like small laptops or small computers, there was need for so much more powerful servers and computers, and that is where like high performance servers comes in, where you have like these huge computers that in its core is still your CPU storage and memory, but when you look at it, it's like maxed out. And in the computing field, you can call this like vertical scaling. For example, your web servers show that the servers used for hosting websites like 20 years ago cannot be the same thing now. It has grown much more. And you see, like, okay, before you might just have needed 4 gig RAM, but now some servers are running on like a lot more. So I want to just go through the so this server, like for example, first the CPU, like have so much, you have large CPU powers that have up to like 64 core counts, which is like individual CPUs processing. Then these CPUs will have large caches, which is like ability to temporarily save data in some specific points. Then you have things like virtualization, which is the ability to now break down your resources into smaller options. So instead of just running serially like your full using your full compute power, you can break it down into like smaller containers and run processes in parallel. Then even your memory, they are more sophisticated. You have error correction checking memory. You have these memories that are now so much more balanced to take both speed, capacity, and reliability. Because before, memory was just for speed, and they had to like depend on the storage. But now we have memories that are so large that they can handle all this, and they're even buffered to have like to the data in memory can be buffered to allow for to reduce congestion. Then we have these huge storage devices. Like in this picture, you can see this server has like multiple hard disk slots, and that's to imagine the amount of terabytes of data these servers hold. And they are hot swappable, meaning like you just pull in and pull out. You can switch your hard disk at will without like shutting down the server. So that is what we see today. Like in your when you think of AI infrastructure, these are things, although much more powerful than this, but this is where it kind of started, having this kind of servers serving and hosting websites. So now when you now think of these servers, I'm sure it can't be your regular Wi-Fi that connects them. So now we have like very powerful network infrastructure for this. We can't even use wireless in the data centers. You have to use either copper cables or fiber optic cables, which are much more powerful. So there are different things that you have to look at, like from the servers itself, the network, the NICs, that's the network slots, the NICs. So they have different types. You need at least like 10 gigabytes minimum for these powerful servers. I need them to be able to support virtualization, and some of them have like multiple ports. You can have in these servers. You can have multiple ports to allow for redundancy and bandwidth and large bandwidth in the for the servers. Then different connectors, like I mentioned, you have different cabling too. You have the copper cabling. The copper cable majorly uses RJ45 connectors. Then you have the fiber optics, which is very fast, and that is what is used today. It's more of it uses light, and you can have up to 100 gig per second speed, so much faster. And this network infrastructure, there are key things that it tries to ensure, which is high bandwidth, like as much data you can go through the wires as much as possible. We have them. And low latency means the response, the communication between devices, they must be so fast. That's why we need them to also be very fast. And that's why we switch to fiber optics, so they can be very fast. And these systems, these networks also have the ability to prioritize traffic. Like you can't just, instead of just sending everything, there are some important traffic, like voice traffic is very important, or some, like if the server is hosting, like for banks, like those kind of transactions should be priority over some less important transactions. So now, as we see that, okay, your regular network, you can scale vertically by like increasing the CPU, increasing the memory, increasing the storage. However, there's always a maximum to that which can do, because at the end of it, it's like a box. The server is a box, so there's just so much you can put into that. So originally, how the scaling now came in is by horizontally scaling, by creating, just adding more servers and using what they call a load balancer. A load balancer is either software or hardware load balancer. It could be like a physical box that you connect in between your servers, before you get to your servers in the network, or it can be software running the routers. And in the as in the net in the routers, that's one of the network gears. And so the goal of this load balancer is to spread the traffic across the servers. Like you can have, like, you can imagine a website like um YouTube right now. You can imagine the thousands and millions of people using that, and you can't just have one server. Definitely not. Although there are more sophisticated technologies used to handle that traffic, application load balancer is one of them. So you spread load balancers will use different algorithms to spread out the the traffic. So it's that round robin, which is just one at a time, or you can have it. It's also intelligent. It can say, okay, the servers with the least connections, the least workload, you give it more per time, give it more of the request. Then you can use some algorithms that, okay, if this specific server started um, communicating with someone, that server continues to serve that client, and you don't give that server's workload to another service, to another server to service. So then for this kind of networks, it's similar to the regular networks we have, but just have the same requirements: high bandwidth, low latency. Then, but in this case, we now have segmentation, where we can isolate our load balancers to a different per resource. Like you can isolate the load balancer for serving user traffic to maybe business traffic. You can segment it. So this is how, like, networks evolved. So as more processing needs to be done, network needed to say, oh, okay, we have these more servers. How can we connect them and maximize the output? So we load balance it across the work across multiple servers. However, with load balancing across multiple servers, with load balancing across multiple servers, you're basically having this case where these servers are still individual devices. And okay, what you're doing is that you're saying, okay, some work should go to this server, some work should go to this server. Although that is good, we're not maximizing the compute. And one of the network's goal is to maximize compute, because that's how we got to AI today. AI is like, you're maximizing, okay, we need to process thousands and thousands of this, and how can we do this very efficiently? And the network has a key role to play. So then network now moved in, there's now a new solution that was created, that is called separation of compute functions. Instead of having one server reply a client and do end-to-end process, You have this server, like in the picture you have here. We logically separate the functions. For example, if a client reaches out to a web server, the web server is in one physical server, then the actual application logic can be stored in a different server, and then the database can be stored in a different server. So you have this separation of logic. Therefore therefore we can more optimally use these devices as much as we can, instead of just having one dedicated device do all the functions. We can spread it across, and this way every server is working as much as it can. So like the network requirements for this is the same, but then is the same. We have high bandwidth, low latency. You have to divide your networks, but before you are dividing your networks based on like, okay, these whole servers are load balanced. You can segment the network, but this time you can now do more proper segmentation. And the network that was now built for this solution for the network that was built for this solution of separation of function was the three-tier network architecture, whereby we said, okay, how can we make sure we can optimize the return time from the user to the servers, but still ensure that these servers can communicate to them, with each other at fast rate. Because before, the servers didn't necessarily communicate with each other; they just communicated to the client. But now you see servers communicating with each other. And how was that done? Like I mentioned, three layers. So the first layer, I think I'll start bottom up instead. So the first layer from bottom is the access layer, which is like you're connecting the end devices to the network. So like the web server goes through the switch or the aggregation layer to communicate with other web servers. And if you now need to connect like a database server, you might need to now go up to the core layer. So because this network, then we have the distribution layer, which now connects the access layers. Then we have the core layer, which is just the high speed backbone that connects the aggregation layer. And this is like your way out of the network. So when a user requests let's say, to a website, it goes through the core layer to the aggregation layer, then the web server. And the web server now, if it needs application logic, it communicates to the application server and then the database server. And this was good at first, but the issue we saw here generally is that the web server needs multiple hop counts to get to a database servers. The web servers have to go up to the access layer, then the aggregation layer, then the core layer before it can get to the database network. So though this was good and prioritized like communication upwards, like to the server, it wasn't as much optimized for communication within the servers themselves. So, but this network requirements, now you needed much more, you needed at least 40 gig bandwidth. Then this introduced what you call VLAN, not introduced, but VLANs are used a lot here, because like this diagram, we had the web servers together, the application servers together, but in real life setting, you can have the web server and the database server connected to the same switch. And to segment your network, you can't do that physically, so you have to use the virtual networks to separate the networks. Then you have to implement like load balancing too. And it's good to notice that most of these network solutions that led up to AI, they are not individual of itself, but they will all work together. Like this three-tier network architecture. For some of the servers, you can now load balance them. Like you can have multiple web servers, multiple application servers, and you load balance across them, but you have still also separated the functions. Then for this network, and in what I just explained, we were separating the functions, but we didn't really talk about how we're now taking care of the need for storage, because as we're processing more, we need to store more. And instead of having the storage like just on the servers themselves, there were network solutions. Like I mentioned, network, we're always helping our storage and compute friends. There are network solutions that were now built to serve to serve this to better take care of the storage. And there's the network attached storage and the storage area network. Basically, the network attached storage is like you just plugging in a very large hard disk to your network. Therefore, every server can just communicate to that network, to that storage when it needs to, and it's just the same Ethernet network. It uses network file system or common internet file system for like sharing of files, and this is just basically like just sharing files. And to the servers is like an externally attached drive, and is inexpensive. But when I move to the storage area network, this is where we build a network for storage, and it gives you like granularity, sorry, of block level access. And by this I mean like when the servers see these devices, to them it is the it's like a hard disk connected to their computers, because it uses fiber channel and SCSI for the fiber channel media and SCSI for the protocol, and it's literally mimicking the connection in the motherboard between the in the motherboard to connect to your hard disk. It mimics that and creates like a huge network for this. However, this is a very expensive solution, but it's very fast, and so it is used majorly for where speed is needed to the servers, to the storage, when you need like to access your data at a very fast rate. Now, like I mentioned, all these solutions that led up to AI. Now I'm coming to like the actual infrastructure the infrastructure that we use today for like our AI. So it's good to notice that these infrastructures, they were just trying to do something, make storage compute storage memory as efficient as possible. And just to give a summary before I come here again, they first, okay, let's add more memory, add more CPUs as much as we can. Then from there, the network had to adjust. Then they said, okay, let's now make multiple servers. The network said, okay, we'll do load balancing. Then the network now said, okay. Then the compute and storage guy said, oh, instead of having just all the functions in one server, let's separate it. Let's have a server for each function. And the network had to also support that and build the three-tier hierarchical model. And now there was now this solution, which is a solution that is used today, is the distributed system. And the core idea is that the core end goal is that you have multiple computers working in parallel at the same time. Like in the picture I have here, we see like a scheduling server which will be connected to all these devices to ensure that okay, all these devices or that the jobs sorry, we have this scheduling server, and the job of the scheduling server is to allocate tasks to each device in the network. So now the tasks are divided and distributed among the nodes based on that based on different algorithms. Then the question then is like, why distributed computing for AI? It's good because parallel processing, like for AI to process the amount of data. Because I personally see AI as not personal, like AI is majorly just data and processing data, reading data, learning from data. So you need to do things at shorter time. You need processing to optimize the CPUs, the GPUs you have. Then distributed computing can scale. Each server in the distributed system is like it works on its own. So it takes the idea of the simple networks where each device works on its own, but now each device works on its own, but to achieve a common goal, and they communicate with each other at very fast speed. So then data distribution. So now each these devices can store data, can now have instead of the dedicated storage so that they previously mentioned, each device has its own storage. But the good thing about this is that it can now like the client A, I'm interacting with client C to extract the data. So you have this communication between the client tolerance when one device dies or when one server like shuts down, there's no issue, because usually there's like I mentioned, like when one device shuts down, other device can take over, and this kind of data, this kind of technique is called striping, where you store chunks of information across the multiple servers, and you don't just store everything in one client. Like the data client A can be processing might be there, but there will be a duplicate in other servers. Therefore, when a server goes down, others can pick up the task and continue. Now, for this solution, they sent it us again. Okay, we have this solution, and networking being the awesome part of the infrastructure provided a solution. And we provided a solution which is the spine and leaf mesh architecture. And this is the architecture used today. So as you see that for this distributed computing, we need the communication between the servers to be as fast as possible. So instead of having like the multiple layered network, we flatten it to just two layers, and every server can communicate to every other server just in two steps. So like in the traditional architecture, we see that for this server, you need to like, okay, one step, two step, three step, four step, five steps, which isn't as fast. But for this case, it's two steps. So from this switch, one and two. So so one, two, one, two. So every switch is connected. Sorry, every server is connected to another server. So it just two hops. So this is like so much faster than the so much faster. So let me go to the next slide. So to give like the details, so this is called the spine and leaf topology. Then for this we can achieve a massive parallelism, because these devices can talk to each other so much faster. Then these devices, they don't just talk to each other using your regular Ethernet. It uses a technology which is called RDMA. And RDMA is that, to explain it simply, each device can talk to each other at a memory level. So that means like instead of them just like communicating with each other, like, oh, a device A is communicating to device B, device A can make changes to device B's memory through the RDMA cable. So this connection is the RDMA interconnect. And RDMA is like including like your switch has to be RDMA capable. Your your cables have to be RDMA capable. The connectors have to be RDMA capable. And sorry, InfiniBand capable. Sorry, I meant InfiniBand. So if each the switches, the connectors, the cables, they all have to be InfiniBand capable. And RDMA is the protocol that enables this memory level access between the devices. So one thing about this network, this solution, that when you have everything interconnected to each other, there's like this, there's like this any kind of any let me explain it this way. So previously, if you have like a design, like for example, you have this network design. Oh, so routing must, like for the traditional architecture, routing must occur at this flow. You must go from access to aggregation to core. But now, when you have everything interconnected with each other, there's this unlimitless amount of network design you can do on top. And it's called like, I don't want to go too much detail here, but it's called like virtualization, where on top of this you can now build multiple virtual instances, where this device, although here talking to each other, we can all look at them as one device. And that is the concept of distributed computing, that all our devices are one device, is one device communicating at that level of speed. Now, so the network did this interconnected mass that every device can now communicate with each other at that speed. And we call this interconnection a network fabric. Then this is now like, so like each network fabric, so this is like a scaled out view. That instead of saying that, oh, each network fabric, so like this circle is like a network fabric, it's like a device. So logically, it's a device. So you can have like 8 fabrics in a data center, and we can have data centers across the world connect to each other at a very fast rate using this meshed topology, because you can see then the fabrics are meshed with other fabrics, then they are meshed with other fabrics outside the physical data center. And to give you a view, so this is the network that today that is powering AI. So you can see this is like the physical, like you can see the amount of cables interconnected to each other. This is what is making AI possible. This is what is making AI possible today. And you can have like, these are just 4 racks. You can have hundreds and hundreds of these talking at very fast rates and making what you now see ChatGPT business solutions that use AI. So this is the end of, I think, and this is it. So this is the end of my tech talk. I hope I didn't talk very fast. I hope I've been able to explain the end-to-end topology and to see. And one thing I wanted to really show is that network AI didn't just happen today. It's been years and years of iterations, years and years of progress, and from we've been learning from each level, each generation of technology, and okay, the next generation making it better and better and better until we now had this spine and leaf topology. And actually, this distributed computing, this spine and leaf topology was has been in existence for a long time, but as the huge with the huge excuse me with the huge boost in AI technologies, this was already ready to serve it. The only thing that the network industry needs to now do is like, okay, deliver this at so much high speed, at faster speeds, instead of normally something that can take will take our time to build. We need to build it faster, increase the capacity, but the infrastructure, the architecture has always been existing. So I think that's the end of my tech talk. Chanel, Chanel, you're muted.
Not me being muted. Um, that was absolutely incredible. I saw so many amazing feedback in the chat. If you all have any questions, please feel free to begin to drop them in the chat. We have quite some time. And I will go first with this question from Lovey Love. What are some tools used to monitor large networks and multiple servers?
Okay, so I think I worked. So I've previously worked at Lenovo, and my role was in the HPC, which is high performance computing. And one of the tools we use, which is actually an open source tool, is called Confluent. So this tool is used is like a network. So we have these tools that are built by different companies. Confluent is like a network cluster management tool. So there are many tools instead of your basic like SNMP protocols, we have these custom built tools that help, like, okay, like you connect all the servers to like this huge box, and you can just what's it called, connect to this box, and send commands to the different servers, shut down commands, restart commands, health check. So those are Confluent is one of the tools. I know there are multiple tools out there. Yeah.
Okay, great. We have another question also from Lovey Love. When training AI data sets, what are some issues a network may encounter keeping up with massive loads of data being sent to the AI model? That's a good question.
Okay, this is a good question actually. So the major difference between like AI, the major fallback we have is that, so previously in networking you can allow for traffic loss, because before like before normally, like if you're using a website, sometimes you see that it's rolling because traffic, sorry, the internet does not need to, how do I explain this? Okay, let me use this. So normally when you're speaking with someone on the phone, you know sometimes it breaks, and what's the worst thing that can happen? The person repeats itself. So the network could allow for some level of loss, But now when you're talking about training models, you need like zero, almost zero loss, because these things are happening at a very fast rate. So we have solutions like software defined networking, where instead of just instead of having each switch, so the traditional way is that every router and switch like does its own computation to say this is the best way to send data traffic. But with software defined networking, you have one large controller that now tells everybody, oh, it tells everybody, okay, send traffic this way. And that one controller has like a picture of the entire network saying that, oh, I know that 100 gig can only pass here, so send exactly 100 gig. Before, it's like trial and model where a router reaches it and says, oh, this is too much for me. Then the network might now send the traffic somewhere else and find a different path. But with this kind of detail needed when training AI datasets, software defined networking is one of the, for most like Google, Amazon, most likely. I don't know about other companies, but most companies generally they use the software defined networking approach where you're more deterministic in saying, okay, I want 50 gig of traffic to pass through here. I want 30 gig of traffic to pass through here, instead of allowing the routers to figure that out in the middle of the process. So that way you don't lose any traffic.
That is so cool. Lovey Love, I hope that answers your question. We have another question from Mr. Darius. What are some networking misconfigurations that you have experienced in the field, and how did you mitigate those risks? Great question as well.
So that's a good question. And I honestly can't remember the last time I had to physically type in configurations, like both from my work at Facebook, Lenovo, Google, like the scale at which these companies do networking, they can't afford network engineers to physically type in. That's where automation comes in. Like instead, you write automation scripts, you test those automation scripts, and they are good to go. So like you can have like labs where you do your tests for your scripts, so to like push configs. So those configs has gone through rigorous testing. So when that is done, when you now go to the field, you're pushing configs that are 100% guaranteed. So that is how like we prevent like network misconfigurations by automated tests. Like you have your config, like you put in a file, then you now run tests in like test beds and ensure that these configs are doing what they're supposed to do. You do some stress tests, and that's how you prevent it. Because the scale at which we do things now, like it's going to hurt you if you try to manually configure. Like from the picture I showed, imagine someone trying to manually configure that one by one. I'm going to do like hundreds of those kind of racks. It's not likely.
Again, awesome question. And I hope that answers your question, Darius. We had a community member drop this in the chat. How do you see the relationship between network latency and AI model performance evolving in the future?
Yeah, I think it's the network is always trying to reduce latency, and I see that just getting better. Like I'm from just Ethernet, where Ethernet that moves like 10 gig, they move to fiber optics, and now we see the introduction of RDMAs, which you're reading like through the network. You're having memory level access instead of just your regular, because normally most times it's just the compute of the server that can access the memory, but having another device access the memory of a different device at such fast speed, I think it's just getting better. And I think I'm also just always looking to see how that can get better. And well, I only see it getting better because the goal of the network team is always to reduce latency, either by architectural design, physical hardware improvements, software improvements. The goal is always, so I see that just getting better and better.
I think that is so cool. You just mentioned fiber optics, and I remember when Verizon Fios came out, and everybody was like, "We have to get Fios, right?" But when you
Yeah.
think about fiber optics now, and obviously like Google Fi, right? Things have changed
Hmm.
completely. So, yeah, I really appreciate that response, and I hope that also answers your question. Another community member put in, how does the increasing scale of AI models impact network design and management?
So yes, so the current, like when I shared my screen, like I think I can share it again. Let me see.
No worries.
Let me share my screen. I think this picture would explain that well. Um,
Okay.
okay, so one of the benefits of like the spine lift topology is the degree which you can scale. For example, before like this access before the traditional architecture, if you want to scale, if they say, oh, we need more servers, you need to increase like the aggregation layer, the access layer. You need to like build a full topology again. But right now, what you just need to do is add a new switch right here and add a new server and just connect it to every spine. So this architecture, this spine leaf architecture is built for scale. Is that you, since it's not going high, you just, as you need more servers, you add a new switch, you add the connections. Although ports do finish, but like this scale is what this spine and leaf architecture network design is was built to handle scale. So if okay, you've maxed out the port, you can build a new. That's how like this picture. This one, you can see the scale at which it can expand, where you just continue interconnecting the data centers to each other at the spine and leaf model. So it's built for scale, and I mean, I've not really read as much, but I'm sure they were seeing AI as they were building and designing these networks because compute has always just been getting bigger and better, and that is why like this spine and leaf topology has stayed for a long while now. And as the AI boom came, it was perfect. We just continue expanding how we do things instead of like starting a fresh design. And like I mentioned, like this mesh network allows us to even have multiple logical designs. So since you have all the network switches connected together, you can now build a logical design on top of that to say, okay, for example, give me a second, let me go back. Since everything's connected together, your actual design can be okay, this is connected to this and this is connected to this and block all other ports. So you can do multiple software level routing and moving of the data since everything is connected either way. You have different parts. So this span and leaf topology was built for good network design and management. So for increasing scale, as AI models increase, we buy more servers, we add to the architecture.
Super cool. Super
Mm.
cool. I hope that also answers your question. Just wanted to say before I go into more questions in the chat, as you all hear us converse, or you may think of other questions, please feel free to drop more in the chat. Especially if you are from Grow with Google, our wonderful program that is helping to scale and grow folks into the IT space, IT support with automation and so on and so forth. Also, obviously, cybersecurity as well. Just let us know that you are tuning in and you are a cohort member so that this can count towards credit for your session. So we have another question. I'm going to start with Darius and then I'll go to the other questions that came in the chat. But Darius mentioned, what skills would you say helped you the most throughout your journey as a network engineer? And what resources do you find useful when it comes to staying up to date with current network trends and technologies? Great question.
Yeah. Um, I think for me, I think it was two things. Then I came into the network space where it was shifting. So like previously, you have to like know BGP, know these network technologies, and that's all you needed to know. You needed to like learn how to do configurations, learn Cisco, learn Juniper, learn all these vendors. But I came into network to the field when that was also switching, and a lot of software was coming in, so a lot of network automation. So my first year in college, I took the CompTIA A plus as like the intro to IT certification because I was like, oh, why not? From there, I took the CompTIA Network Plus. So the networking field has a lot of certifications to I see the benefits for certifications because it helps you like a guided learning path. So I took the A plus, then I took the Network plus, then I took the CCNA, then I'm currently practicing for the CCNP. So that was what helped my network understanding. This guided, except from like college, but like this separate study, it guided my learning path towards like, okay, I'm learning this now. Like I was building knowledge on top of each other. So outside just having like, oh, this pretty paper, that guided learning path was very good. Then on the side, I was also learning automation. So I think one of my summers when I didn't get an internship, um, I picked up Python from like a Udemy course and I learned Python. Then from there, side project. So I think so having that 50-50 like network knowledge and automation capability, it really helped me. Like it really helped me like, okay, because most companies now, when they're hiring for a network engineer, they're not just even hiring for your network knowledge. They need you to know how to code to automate the network technologies you have. And also they want somebody, they just sometimes they don't just want a software engineer, they want someone that has that network background. So I think those are the two things that they are helping me because I'm still growing in the field. I'm still like I'm definitely not where I think I should be, so it's those are things I constantly try to keep on. Although, like, because I'm currently reading for my CCMP, I try to keep up to date with the network technologies happening like in the industry, but I also try to add learn how to automate anything that can be done manually. There's definitely a way to automate it. I think with that mindset. So even as I'm reading technologies, I'm like, oh, okay, I'm kind of learning it not just to learn how to configure it. And to be fair, I don't even pay as much attention to like the configuration, but I'm trying to understand the design, the design concept, because that's knowledge that is now needed when you're automating. So I think that's the best thing. Like, just make sure you're learning on those two.
I think that is an awesome explanation. Um, you know, as a member and a mentor, member of Black in AI, and obviously a mentor as well. Um, and kind of going in tune with this question, but are there other pieces of advice or maybe resources that you would highlight for individuals that are aspiring to be network engineers as well?
Um, Regarding advice, I'll just say always keep growing,
Mm,
keep learning. Like, as once you stop growing, there's a problem. So
mhm,
just make sure you're always learning. You're always learning. That's something I would always tell someone. Like, in then if you're network engineer interested in AI, like I was thinking about something one day. I'm like, there's AI for the network and there's AI by the network. So what I just explained, like the whole architecture was like AI by the network. Like it's the network enabling AI, but it's also
mm,
like AI for the network, where, like I mentioned earlier, like there's this software defined networking. So all that process is also AI, where you're making the AI will calculate the best path, like this huge brain will calculate the best path for the network, for network traffic. So that is also some level of AI processing, like, okay, to take a picture of the network, a logical picture, then it says the best path to get from point A to point B is through this path. That is also AI. So like the there's so much that AI can like if you're interested as a network engineer, if you're interested in working for AI, to just really for specific resources, honestly, I can't give you specific because there's so much. Like there are, if you go on YouTube, there are wonderful network engineers that are always giving wonderful advice, giving
mhm.
tutorials, Udemy courses. Like that's how I learn. That's how I study through courses, like online courses, YouTube videos. So that just keep on learning. I think that's our advice.
Excellent advice as well.
Yeah.
We had one more question in the chat from Renee. Thinking about cloud, can you explain why some say AWS may not be as secure as a cloud network? And how would you rank the cloud networks as far as security?
Well, I
I,
honestly believe I believe the cloud network is very secure.
mm,
Um, I think it depends. This thing that depends on the person really, because the idea of the cloud is, oh, this network infrastructure, you're running it on premise, it's too expensive to run yourself. Why don't
Mm-hmm.
you outsource it to someone else? So then you outsource it to a company like Google. Google Google has their own data centers. Then they provide you access to their infrastructure. Now, not to be biased, but if Google, okay, or AWS, you gave the example of AWS or GCP. Let's say I'm biased. If GCP can't secure your data, I'm not sure a network engineer on his own might do a better job because of the amount of money, the amount of resources, the manpower that comes to securing these data centers. I don't think um, you running it on yourself, you should. I don't think, although you can run it and be very secure, but I don't think there's a reason to not trust these corporations. Now, if you're using, that's why like I always personally advise like use the popular ones like GCP. Like that is a trusted provider. But then when you're now talking about okay, it's not secure, it's now okay, what provider are you using? Are you using like a no-name provider that nobody knows? Then that is where there are issues. But I believe that like AWS, sorry, GCP or AWS, either one is very secure. Then the reason why some people might say it's not secure is first of all, if there's this feeling that oh, if I don't know where it is, I don't trust it. Like since I don't have it physically with me, there's this like lack of trust that someone might have saying, okay, I have my servers in my room, in my server floor. I know where it is, so I trust it, but I don't know where they are saving my data. So that could be a reason. But I really don't. A lot of companies use these cloud providers. So I think they've gained, maybe at first, but now I feel they've gained a lot of credibility. And that's also something I wanted to say, like in the beginning of the call, that I didn't. And as I'm here, I'm not representing Google, like officially. This is everything I said is my thoughts. I use public information. I'm not like representing Google in every way, shape, or form. I don't know. I forgot to say that in the beginning. I just also wanted to just drop that here. Yeah.
No
I
worries
hope
at all. And no, you're totally fine. No, no worries at all. Totally support that, and I understand. But yeah, no, it looks like those were all the questions in the chat. We have about 1 minute, so please, we'd love to know how we can continue to follow you, stay connected, feel free to share with the team.
okay, so well, my LinkedIn is available. I think
Mhm.
I think you have it,
Yeah,
or I can.
I can absolutely put that
Yeah.
in the chat.
Yes. Then I have a blog that I manage. Like, I loved. Yes. So I love networking. So as I'm studying, I'm always okay, trying to explain things. And normally I had this like in my bag, in my closet somewhere. I have these notebooks of just explaining things for myself. So I said, why not? Late last year, I said, why not have that like available and like in a organized database. So I started a mini blog, and every now and then and I've been studying for the CCNP. I've been updating the blog on like some technologies I find interesting. So I think the name of the blog I can add it here. Networks by Muna.com. So although most of the content there, I assume you're a network engineer, so I might not explain because this is also my personal notes. So I just
Mhm.
assume that oh, you have some sort of background knowledge. Some I explain detailed, but some I just I even give like a preface that okay, you should understand this coming into like the to understand this blog. This prior knowledge is required. Then I go in, but I try as much as possible. Like the concept I'm talking about, I try as much as possible to explain it, open it up, and explain it as much as possible. So when I come back to it, I read it. I'm like, okay, this is how this actually works. Instead of going through the Google search again, I already have my notes. So basically,
I
so
think
yeah.
that's so cool.
Hmm.
I love that. So it's almost like your own diary of all of your learns, like your
Yeah.
learns around. Okay. That's very, very cool. So here it is right here on the screen. You all can feel free to visit this wonderful blog by Muna. I also highlighted Muna's LinkedIn, so feel free to connect there as well. Muna, thanks so much for your time, your
Thank,
wisdom, and all of the energy you put into this fabulous presentation.
thank you so much for having me.
You are
Yeah.
so, so welcome. Have a good one.
Have a good one. Bye.
Alrighty. All right, y'all. Thanks again so much for tuning into this amazing presentation with Muna. Please go ahead and follow him, connect with him on LinkedIn. Again, I'm going to go ahead and highlight the blog. It's nothing more exciting than being able to learn from or through the lenses of others, right? Others may say like learning from others, other people's mistakes so that you don't have to make them. So please lean into that incredible resource as well. As you know, we have workshops happening every Wednesday up from now up until the end of September this year. So, our next workshop will be leaning into Women's History Month. Okay, we're partnering with Women Tech Makers of Google, and we're going to be highlighting some incredible women. So stay tuned for those sessions. If you're already on YouTube, you can probably already see the lineup. Please make sure you just go ahead and give us a thumbs up. Make sure you click subscribe and hit the notification bell. Support our community, y'all, while we bring you all incredible content like this as well. But until next time, au revoir, everyone. Bye.